6.4, inverse functions. An inverse relation is a relation that interchanges the input and the output values, meaning input being the x values, output being the y values. It also interchanges the domain and the range. Since the domain is all the x values and the range is all the y values, the input and the output, those are lined up, those would also be interchanged. So in order to find an inverse relation, what I'm going to ask you to do is think about looking at the function that you're given. What is happening to x? If I plugged a number in for x, what would be my steps in evaluating to find an actual end value is kind of what you could be asking yourself as you go through that. The big key here is you must follow order of operations. Once you have, and I'm gonna actually show you, write out those steps for step one. What would be the steps that you would have to take following order of operations? Then for the second part of it, you're going to reverse the order of the steps and do the inverse operation for each to find the inverse relation. And that's what you're going to use to actually write the inverse relation. So number 3, we're given an original relation, y equals 3x minus 5. So going through step 1, like discussed above, I would know that if I plugged a number into x, the first thing I'd have to do is multiply that number by 3, and then I would subtract 5. Now, reversing the order and using the inverse operation, instead of subtracting 5, I'm going to add 5 for the first step in the inverse. And then instead of multiplying by 3, I'm going to divide by 3. So now what this allows me to do is follow the steps in the inverse column to write my new function. So starting with just an x, I would start with y equals x. I would add 5 and then divide everything by 3. It would look like this. Y equals x plus 5 all in the numerator, 3 in the denominator. If I add the 5 first, then I divide by 3. When I divide by that 3, it's everything that's already in my equation that has to be divided by that 3. Now what I'm going to ask you to do is also make sure this gets put into, if it's linear like this, gets put into slope-intercept form. It's easier for us to use later on if we needed to. So that means we're going to kind of think of this as being each individual part of the numerator divided by that 3. And then I would just write it a little bit more like we're used to seeing it. Y equals 1/3 x plus 5/3. This would be my inverse function of the original that I was given. So part B kind of follows the same idea. The original, the steps using order of operations would be to multiply by 12 and then add the 2. So reversing the order of the steps and using the inverse operations, inverse of adding is subtracting, so that's got to be subtracting 2 first. And then inverse of multiplying is dividing, so I would be dividing by 12 for the second step. So when I write my inverse, it would first start off looking like y equals x minus 2 all over 12. Now I'm going to split those and write it as x over 12 minus 2 over 12, because now this will allow me to also reduce, and I can get y equals 1/12 x minus 1/6. Now, if we want to find the inverse of a function when we're given a graph, sorry about that. If we want to find the inverse of the function given a graph, we would need to first be able to write the equation of that graph. So in this case, since this is a line, first thing I need in order to write the equation of a line is the slope. So remember, slope formula is y2 minus y1 over x2 minus x1. And I can pick any 2 points that I want off of this graph. In this case, I've chosen the x and y intercepts. So if I plug those into my slope formula and work my way through and reduce, I would find that the slope is positive 1/2, which I could also tell on the graph by counting the boxes since I'm given the full graph. But again, I wanted to show this just in case you needed it. And now I could also see that my y-intercept is the point 0, -3. And remember, this -3 would be the b value in slope-intercept form, which is y equals mx plus b. So the 1/2 is going in for m, the -3 is going in for the b. So the equation of the original function is y equals 1/2 x minus 3. Now once I have my original equation, I can go back to our normal process of first thinking through what are the steps using order of operations that would be going on in the original. First step would be to multiply by 1/2. Second step would be to subtract the 3. So now for the inverse, I have to reverse the order of those and use the opposite, or excuse me, inverse operation. So inverse of subtracting is adding. So we're going to add 3 first. And now we have to remember multiplying by 1/2 is the same as dividing by 2. So now if I'm thinking dividing by 2, what's the inverse of dividing? That's multiplying again, but it's multiplying by 2. So here's what it would look like when you add the 3 and then multiply by 2. Notice I have parentheses around the x plus 3, because when I multiply by 2 in that second step for my inverse, I have to multiply everything that's already in the equation by that 2. Now I would want to distribute that 2 to be able to simplify and get my equation into slope-intercept form. All right, so now a few examples that use power functions. Notice these also have function notation being used. The f of x is the same thing as y, though, so it's not going to change anything that we're doing. So in my original here for part A, what is happening to this x using order of operations? The first thing that's happening to it, the only thing, is that it's being cubed. Now the inverse operation of cubing something is taking a cube root. So now when we go to write our inverse function here, since it's using function notation, we can use the inverse of the function notation by putting just a simple -1 exponent after the f in f of x. And now if we start this with an x, you always want to start with the x. You are just taking the cube root of that, and this would be the inverse of that original. In part B, following order of operations, the original would have steps of using the 7th power and then multiplying by 128. The inverse, again, go in the reverse order and use the inverse operation. We would be dividing by 128. And then the inverse of taking a 7th power would be using the 7th root. So now what this would look like, if I start with my inverse function notation here, I would start with my x variable. I would divide that by the 128, and then I would take the 7th root of the entire thing. But now we don't want to just leave this. We want to simplify this. So that means that I want to think of this as the 7th root of x over the 7th root of 128. And we could really quickly check with our calculators, is 128, does it have a perfect 7th root? We can try to do that. And this time it would end up being that it does. So I would want to take that root. So I'd have the 7th root of x over the 7th root of 128 ends up being 2. Whoops. Ends up being 2. So now the final answer for this inverse would be the inverse of x is the 7th root of x over 2. Now in part C, adding more and more steps. Be really careful here. Make sure you're following order of operations. If I were to evaluate this, if I were able to plug a value in for x, the first thing that I would have to do by order of operations would be subtract that 2 because it's inside the parentheses. After that, I would square that value. Then I would multiply by the 3 in the numerator. And then lastly, I would divide by the 4 that's in the denominator. So now reversing the order and using the inverse operation of each of these, the first step in the inverse would be to multiply by 4. Then we would divide by 3. Then we would take the square root of all of that. And lastly, we would add 2. So how you would kind of build this inverse, okay, once again, you would start with the inverse of f of x. You start with your x variable. Now the first thing I have to do is multiply that by 4. So that's shown there. Now I have to divide all of that by 3. Now I have to take the square root of all of that. Now here, since this is a square root, it's an even root. We need to make sure we include the plus and minus in front of it. And then adding 2 on the end, notice it's outside of that square root because it's happening after the square root. Cannot put it inside. That means something completely different. And then this, I'm not going to worry about having you simplify any further than that. We can just leave it right there. I'm more interested in, can you use those steps that you're writing down for the inverse correctly and make the correct equation? But again, big time key here. Anytime you're using an even root, make sure you include that plus or minus. All right, we're going to skip over number 6, so go ahead and just cross that out or just leave it if you'd like. Now we have what's called the horizontal line test. You may be able to think back to when we first were asked the question, is a certain equation, is a relation a function? We use what was called the vertical line test to check whether or not it would be. Now we have what's called the horizontal line test, and this is used to check whether or not the inverse of a function is actually a function. So what this entails is being able to sketch a graph for an original function that's given to you, and then we would use the horizontal line test to see if we could find a horizontal line that intersects the graph of the original function more than once. That would tell us whether or not it is a function with the inverse or not. So notice I've got this extra note here. Please make sure you write this down. We've done different graphing of different functions in the sections 2-7, day 1 through day 3. That was where we did the absolute values. Section 4-1, day 1 and day 2 is where we looked at graphing parabolas or quadratics. And then 5-2 is where we talked about the shapes of different graphs, going back to linear, hitting quadratic again, talking about cubic, talking about the quartic, and actually we even hit on the constant that I didn't mention at the beginning. So now what's going to be key here is I'm not going to ask you to graph these perfectly. What I'm going to say that you need to do is you need to get a good sketch of the graph. So what has to happen is after you go back and look at these, or hopefully you even remember a good amount, when I give you the function f of x equals x cubed, you have to be able to remember what shape that graph is. If you can't, you could make a list of an x and y chart and actually use your calculator and plug things in, but it's much more efficient if you can remember what the graphs look like. And I'm going to help you review that right now anyways. So if we just have an x cubed, there's nothing else in this x cubed. This graph takes this shape, okay? Now, we did talk about cubics where it starts having a hill and then into a valley, and we'll talk about when that happens in a minute. But this graph would be what the base graph is for an x cubed function. Now, if you can imagine this, or even after you draw this, lay your pencil down horizontally on the paper, move it from top to bottom or bottom to top. At any single location, does that horizontal line intersect this more than one time? It does not. So since the horizontal line only hits one point at a time on this graph, we can say yes, the inverse of this is also a function. When we move to our second one in the top row, notice we now have another cubic function because its largest degree is 3. But now we have all this extra information, especially the x squared and the x terms. What this causes in our cubic graph is now for us to have that hill and that valley. This plus 5 on the end, that you can always use as your y-intercept. So this point right here where it crosses the y-axis, if I want to be a little bit more precise, that would be a positive 5. So make sure it crosses up here instead of maybe down here or at 0. Now use that horizontal line test. Is this inverse a function? This would not be a function because we can draw more than one, but at least one line that would touch this graph at more than one point at a time. So down here it's okay, but once we get up here, we would start hitting 2 and 3 times. That would cause this inverse to not be a function. For the third one in the top row, f of x equals x squared, this is called a quadratic. Hopefully you guys remember that a quadratic graph is called a parabola, and we don't have any extra values here, so we know, or should know, that our y-intercept is 0, 0, and this would be opening up because it's a positive a value. Okay, we have to go back and review all those things. Now if we do the horizontal line test, is the inverse of this a function? This inverse would not be a function. There would be an infinite number of places where a horizontal line would touch that graph at more than one point. For the first one in the second row, hopefully you recognize this as a linear function. There is no exponent larger than 1. So this is just slope-intercept form. Graphing this, our y-intercept would be -5. We would have a slope of -1. If you do the horizontal line test on this, would the inverse of this be a function? The inverse of this would be a function. There would be no horizontal line that would intersect this graph at more than one point at a time. The second function given to us in the second row, this is already in factored form, or otherwise referred to as intercept form. But if you think about this, if you were to double distribute or FOIL these two binomials back together, this would be a quadratic equation because x times x would give you x squared. But we don't need to do that necessarily because we have this already in that intercept form. What this allows us to say is that 2 and -3 are the two x-intercepts of our graph. And this would also be a parabola since it's quadratic, and it opens up because x times x is a positive x squared. That a value would be a positive 1. We would be able to sketch our graph a little bit more accurately, still not worried about being perfectly accurate. So we could put a point at -3 on the x-axis, put a point at +2 on the x-axis, draw that parabola opening upwards, and that would be a great sketch. Now, is the inverse of this function a function? This would not be a function. There'd be, again, an infinite number of horizontal lines that intersect this graph at more than one point at a time. Now, finally, the last one in this second row, and the last one on your note sheet, this is referred to as a quartic, because of the exponent being a 4. And that's even degree. Remember we talked about even degree versus odd degree? Even degrees take the shape of either a W or an M, all depending on whether the lead coefficient is positive or negative. This time it's positive. So that would be a W shape to be opening up. The last value here would be like your y-intercept. So we could sketch a somewhat accurate graph. If this scale of this graph allowed this to be a -6, the important part is that it's underneath the x-axis and the W shape is opening up. Would the inverse of this function be a function? The inverse here, again, would not be a function. There are numerous, actually infinite, horizontal lines that would intersect that graph at more than one point at a time. So now this video is finished. If you need to go back and look at anything, please do. The homework assignment that must be submitted by class time on Friday is just 1 through 11 out of your homework packet.